Welcome back, students, to our Chemistry 2620 video notes. In this video, we're going to look at Chapter 23, which is organometallic compounds. These compounds you've already seen before. You have already seen Grignard reagents, which are organomagnesium, and Gilman reagents, which are organocopper. We've spoken briefly about organolithium reagents as very dangerous and very strong bases. What makes these so special is they all have one thing in common, and that is that they contain a metal, and that metal ends up having a low electronegativity. And what ends up occurring during the course of this is, no matter if we're talking about a compound that has lithium here, magnesium, or copper, every single time your polarity arrow looks like this. And so what that really means, and I'm going to redraw this in red really quick, and what that really means is the lithium is lower in electronegativity than the carbon, and so the carbon has the partial negative, and that's not common. Almost all of the time that we see a polar bond, we're seeing a polar bond like this, where the external atom, the attached atom, not the carbon, so the heteroatom is the one that has the partial negative. And in this case, it's the carbon that has the partial negative. So let's look at some reactions where you might see organometallics. So first of all, these are ones that you've already seen before. You have seen how Grignard reagent can react with an acid chloride to add two methyls. So these two methyls were from the methyl of the magnesium bromide. Gilman reagent is not as strong, and so it is only capable of adding once. And so you're going to see one addition here from your Gilman reagent. Your Gilman reagent could also be used in Michael reactions. And in Michael reactions, remember, this was a 1,4 addition where you had a super sneaky hydrogen add to the O, but that ended up creating an enol, and that tautomerized. So here we see the methyl is adding to this position and getting rid of that pi bond. If you don't remember that, then go ahead and go back to chapter 21 where we saw that. It was the end of chapter 21. So we've already seen reactions that use organolithium, organomagnesium compounds. What we haven't talked about is very much about how they can form. And so these compounds are very ionic. They're more similar probably to an ionic compound than a covalent compound because the electronegativity difference is probably going to be quite high. Now, I don't know lithium's electronegativity off the top of my head, but I believe carbon is 2.1. And metals are naturally lower, right? They're naturally less than 1. And so that's why we say that these bonds are quite ionic, is usually they have a pretty high difference in electronegativity. Now, that being said, and now that I'm thinking about it, carbon might be 2.5 and hydrogen's 2.1, but that's okay. What we really need to recognize is sometimes you might see these compounds written instead as if they are ionic. And if you do see it written like this, don't freak out. They're just trying to say that the carbon-lithium bond is so polar that it's almost like the carbon's a carbanion. The same thing can happen with Grignard, where people will sometimes draw your Grignard in a similar fashion, like this, where again, all they're saying is that carbon has so much electron density, that it can behave like a carbanion. So let's talk about how we could prepare these organolithium compounds. Remember, lithium on its own is very reactive, right? It's in the alkali metal compound. It's so reactive that you can't even store it in air. It has to be covered in oil so it doesn't react with the water vapor in the air. So when this happens and you add an alkyl halide with some lithium, what you're expecting is the same number of carbons, so 1, 2, 3, 4, 1, 2, 3, 4, and then your lithium. The same thing is going to happen here, which is quite interesting because some of our other reactions we've talked about can't happen at sp2 hybridized carbons, and that's not the case here. So let's talk about how to prepare an organomagnesium compound. You have actually already seen this preparation before, but you've seen it specifically with using a bromine as the halide. So remember that this ether, this diethyl ether, has to be anhydrous during this process. And what ends up happening is essentially the magnesium inserts itself between the carbon and the bromine. If we change the bromine to a chlorine, the same thing is still going to happen. So now the magnesium inserts itself and then you have the chlorine. When we start looking at these reactions, you just need to be aware that there's really no significant change between the one that you've already seen before and switching out what that halogen is. All right, so let's talk a little bit about how organolithium and organomagnesium compounds can behave as really strong bases. So these compounds are very strong bases. Remember that the acid, the conjugate acid of these, is an alkyl group. Alkyl groups or alkyl compounds have a pKa of 50, and that's very weak. So if you're able to pull a proton off and create the conjugate base, then that means that the conjugate base is going to be very strong, because the strong acid has a weak base, and then the contrary is true, right? So the weak acid has a strong base. So what that means is these compounds, if there's any acidic proton present, bam, it is going to react with that acidic proton. So your Grignard is going to come in and attack here well before it would attack anything like a ketone. So in this case, what we would end up with is just a very expensive way to get an alkyl group as well as a magnesium X and hydroxide. So what this really relates to is if you had a ketone that you wanted your Grignard to react with, and you wanted maybe to add a benzene ring, and then you had some water present by accident. Maybe you didn't use anhydrous ether as your solvent. You used regular ether. Mind you, anhydrous means without water. So if this were to happen, your goal, of course, is to have this type of thing occur by the magnesium attacking like so. The problem is the Grignard reagent is such a strong base that it's going to behave as a base well before it behaves as a nucleophile. So instead of getting those arrows, you're going to get this arrow instead. And then instead of getting the product you wanted, you're going to create benzene, a very expensive and time-consuming way to create benzene, and then magnesium bromide plus hydroxide ion. So that was disappointing. So instead, you'll just run the reaction without water. So let's look at how we want them to behave. We want these to behave as nucleophiles. And so when we look at some past reactions that we've seen before, we've already seen that no matter what the R group is, our Grignard will add like so. We have not yet explicitly discussed the epoxide ring opening, but we did in Orgo 1, so we should be able to do it now. Remember that this bond is polar toward the oxygen, leaving a partial positive at those bottom two carbons. So what will happen is your Grignard is your nucleophile, the carbon that I'm pointing to is your electrophile, and so this opens up that ring. So what you do is you're essentially making a bond between carbons, so your R group is now going to be attached to this carbon right here. That carbon is attached to this carbon, and this carbon's attached to an oxygen. And remember, you have a proton source, so we're going to protonate that. Then, if we change from a ketone to a ester, remember that your Grignard will react twice when you have a good leaving group here. And so what will happen in this case is you would get 2 additions of your Grignard. In this final reaction down here, when a Grignard encounters a nitrile, what ends up occurring is you get this as an intermediate. Once this imine is protonated with the acid, it goes through another set of series of steps. All right, so pretend that didn't happen yet. So it goes through a series of steps where you protonate it, and it goes through a hydrolysis reaction, and then you get an oxygen there. So I think we saw this in our imine and enamine chapter, but if you want to look it up, just look up hydrolysis, I think I switched those, of imine. So let's look and see what's next. All right, some more information now about Gilman reagents. So your Gilman reagents are lithium dialkyl cuprates. Cuprates is just the old word for copper. And so what happens is that the copper has 2 alkyl groups attached to it. That overall has a negative formal charge, and a lithium hangs out nearby. So this is an interesting reaction, because one thing that you might be thinking is, why is it that we can't just start here and add the copper right away? And the answer is that the copper is not strong enough to do that reaction. So what needs to happen is something called a transmutation of metals, where we end up putting a lithium here, which is then quite reactive. And then once we have that very reactive lithium in, we can put in the copper. So what will happen during the course of this reaction is your copper will be kind of the central piece. You'll have 2 phenols on either side, and this overall has a negative formal charge, and then your lithium will hang out nearby. And so usually we don't draw the whole darn thing out like that. Usually what we do to shorten it is write the R group, say that there's 2 of them, say that there's a copper, and say that there's a lithium. So that's how we would tend to draw the Gilman reagent. All right, so these reactions of Gilman reagents that we've seen in the past, we actually haven't, I think, seen the one right here with the ketone, because what you might expect to have happen would be something like this, because that's what happens with Grignard. But it turns out that the Gilman reagent isn't strong enough to undergo a reaction here. So Gilmans do not react with ketones. They do react with acid chlorides and other carboxylic acid derivatives, though. Now, in addition to kind of saying they don't react with ketones, when we see this alpha-beta unsaturated ketone down here, do recall that these will react, but they're going to add to the 4th position. They're not adding to the oxygen there, but rather they're going to add to this position. So you end up getting the oxygen here and another R group here. Okay, so then as we get toward the end of this chapter, let's talk about another thing that Gilman reagents can do. Gilman reagents can actually undergo SN2 mechanisms. So they can react with organohalides, so like this, plus whatever your Gilman reagent is, let's just put a general R group there, to create new carbon bonds. So here I had 1, 2, 3 carbons, so 1, 2, 3, and then my R group attaches, right? And you're left over with some copper and lithium. So this is called a coupling reaction. A lot of reactions that add 2 carbons together are called coupling reactions. They usually take place in low temperatures, and when we say low, I mean like negative 78 degrees Celsius, like real low. And so the interesting thing here is that the R group of the organohalide can be not only methyl and primary, but also vinyl or aryl. Remember, vinyl meant this. So this is your vinylic position. But of course, like all of our regular SN2 reactions, the alkyl halide may not be secondary or tertiary, because then you won't get an SN2 reactions, rather you'll get an elimination product. So down here is a mechanism about how they think that the Gilman reagent does this, because it's not quite like a full SN2 mechanism the way that we would normally draw. The idea is that your Gilman reagent, where the pair of electrons that you care about is on the copper, that's your nucleophile. It attacks your electrophilic carbon and you force out your leaving group. So that part's really typical of an SN2 reaction. The problem is the Gilman reagent that has the copper on it would then be in your final product. And so what ends up happening is a little bit of a rearrangement here so that you get that carbon-carbon bond at the end. All right, so our last reaction of this chapter is a type of reaction or a type of reagent called carbenes. Carbenes are super unusual. Carbenes look like they shouldn't be possible. They look like this. And a lot of times we see some interesting ways to make carbenes that I think we saw one in the end of Orgo 1, but I'm not sure if everybody saw one at the end of Orgo 1. So in order to make a carbene, you usually start with a carbon that has 2 R groups attached, and then in Orgo 1 I believe we used iodine groups. Then you add something to this. One thing that you can add is butyl lithium. That's not the reagent that we used in Orgo 1. In Orgo 1 we used a copper reagent. And what ends up happening is you get the carbene, which is relatively unstable, plus the lithium iodide that we don't care about. So what carbenes do is they tend to make cyclic compounds. So if you start with something that has a double bond and you add the carbene, which you make in situ, which means in the flask, what ends up happening is you get a cyclic compound where this carbon right here was the carbon of the carbene and the R's are still attached. Now, when you look at this reaction, if you took Orgo 1 with me, I would put this stuff kind of down here, and with the I2s, the biggest mistake in Orgo 1 is students writing the halogens here instead. But your halogens are just a good leaving group for the course of the carbene reaction. So those aren't there, and that's not possible. But instead, you get this cyclic ring. You're going to go into it a little bit more when you look at the problems in the textbook, where they're going to have more complex alkenes. They could have cis alkenes, they could have trans alkenes, and they could have alkenes within bigger molecules. But the core concept is the same. As always, thank you for your attention. This is Katoni signing out.